So today we're going to talk about the MST, minimum spanning tree. So we learned about what is BFS and DFS. Okay, we are getting closer to the actual. We're going to go deeper on the graph. Okay, so we in the DFS and BFS, we did all the edges are equal, then the basic DFS, right? Then what if the weights are the edges are weighted? And how can I make the overall something like from one point to all the others? That is MST. Some noises coming out. Okay. So beyond the DFS or BFS, there exists an alternate universe of the algorithm for edge and weighted graph. And our adjacent list, we understand what is adjacent list, right? Who's one neighbor who has a link. Okay. So our adjacent list represent quietly support this graph. So from me, and who's my next? And what about weight? Okay, then I can make an edge node. The minimum spanning tree is a tree, is a connected graph with no cycle. This is critical, with no cycle. MST should not create the cycle. Okay, spanning tree is a subgraph of G, which has the same set of the vertices of G, is a tree. So MST of a weighted graph G is a spanning tree of G, whose edges sum to minimum weight. Okay, this is then we call the minimum spanning tree. There can be more than one MST in the graph. So find the minimum spanning tree of this vertices. How can I find? So how can I find the minimum spanning tree? Minimum spanning tree meaning me from everybody with the minimum cost. Then I can reach everybody. I can reach, so any node, any random node can reach everybody.
I think we can connect the center node, center point to.
Okay, so Youngjae is trying. So give me a second. So let's think about for 1 minute, and give a higher priority to Youngjae.
Okay.
Okay. So think about 1 minute. So you understand that, so right? So find the minimum spanning tree of this given environment. So Youngjae said, oh, starting from this guy, this guy. No. So minimum spanning tree should start at random point. Right? Given point. So I should find from this guy to MST, this guy to MST. So we don't know geographical information of this node. Okay. So let's think about for 1 minute, then we can discuss.
Professor,
Okay, so this is how it's done. Okay, so Prim's algorithm in a pseudocode is during the execution of each vertex V, either in tree or fringe or unseen. Fringe meaning in one edge, one hop away. Okay, so unseen is you are not discovered yet. So Prim's MST with the graph G, select the arbitrary vertex S to start the tree from. While there is still non-tree vertices, I'm keep selecting with the minimum edge between tree and non-tree vertices. So among the candidate, I'm choosing the minimum weight. Then add the selected edges and vertex to constructed T tree prims, unless it is not violating my rules. Creating this does not create the cycle. Okay, so this creates a spanning tree. So since no cycle can be introduced, but is it minimum? How can you guarantee it's the minimum? Any thought? Can we prove this? So in the algorithm, in a CSE373 is like proving, meaning persuade someone with the proper basis or showing the counter example. Okay, so let's do by a counter example, what we call the contradiction. So if the prim is not correct, there must be some graph G where it does not give a minimum spanning tree. If so, there must be first edge X and Y, the prims add such that there is a partial tree that cannot extend it to MST, right? What does this mean? So let's say your tree was built in this way. And let's say you want to edit this. By adding this, you have to disconnect it, right? Because by adding this, you are creating a cycle. If it was the minimum spanning tree, this shouldn't be added at the contention of this edge extension, right? So if X and Y is not MST, then there must be path between X to Y. There must be path between this way, right? X and Y is connected by this path. Let me erase it. X and Y is connected either this way or this way. So let V1 and V2 be the other edge on this path with the one end in the B prime. Replacing B1 and B2 with XY, we get the spanning tree, okay, with the smaller weight. Since W of the weight is V1 and V2 is a bigger than XY, thus we did not have the MST. So which means if this was connected, then it shouldn't be the MST. If this is connected, this shouldn't be an MST. Okay, it does not make sense by the contradiction. So if W and V1 and V2 are the same, then we choose the by a tie-breaking rule. But there's still the same weight. The tree is almost same weight because this weight and this weight is same. So we couldn't make the fatal mistake by picking an XY. So by the contradiction, the primed algorithm is correct. So go back to the point. So how do we prove that? If it is a smaller value than this, then I'm adding this. Okay. If the MST, if this is not MST, then this should be added rather than doing this. In the complete view, if this was connected, then V1 and V2 is never able to be added. Why? Because it breaks the rule. By adding this, it creates a cycle. Okay. Otherwise, if there is a path in between here, then X and Y is not, this path is not the minimum spanning tree. Okay. So the basic primed algorithm is choosing local best, choosing local best, and choosing local best. Okay. By repeating the local best, maybe you are not the optimized one, but you cannot choose the worst one. So primed algorithm, by choosing the local best, eventually reach the MST. Okay. So how fast is the primed algorithm? So primed algorithm performance depends on what data structure we are using. So in the simplest implementation, we can simply mark each vertex as a tree and a non-tree, tree and non-tree, and search always from the scratch. So select arbitrary vertex to start. If there's a still non-tree vertices, select the minimum weight edges between tree and fringe. Now we understand. Oh, my graph is here. I have candidate. Candidate are on my fringe. Among fringe, I'm choosing the minimum. Then I can extend my graph. Okay. So this can be done in the big O NM. Why? I have to visit all the vertices, and I'm choosing among the candidate. M is a little bigger than M by M for I do 1, 2, all the vertex for M to 1, 2, M. Then if it is valid and minimum, extend my graph. So it's NM by doing a DFS or BFS. DFS and BFS on my fringe list. It's more like BFS. It's your choice. And to loop through all the edges among the fringes with a constant time per edge and total n iterations. So primitive algorithm, let me check this. So Prim's spanning tree, there's a full text you can read through and all the source node and step by step. Okay. So you can run it through. This is what we exactly learned in the classroom. Okay. So it's basically while tree, the tree we are building is not yet spanning tree, meaning while I'm discovering all the edges and find the edge that is safe, safe meaning not create a cycle, to add to a tree and add the new edge to a tree. That is MST for prims. So this is primed algorithm for MST. Okay, prims analysis. So find the minimum weight fringe edge takes big O n time. So it's smaller than n, right? I have to check my vertices among the candidate, which takes n time. Because I have numbers in here, then there is a candidate. It is function of n. After adding vertices v to the tree by running through its adjacent list, it checks the cheaper or no, meaning. So let's say I'm adding this guy, and by adding this, do I make cycle? I have to check it first. Then I also make check. If by doing this, do I make another link cheaper than this? Then what can I do? Let's say this one. Let's say my graph, it looked like this, and there is a path in here. Then by adding this path, which means if it is a cheaper, then I can disconnect this guy. Okay, so it updates the distance value, breaking it and reconnect it. Total time, is it cheaper? Is it cheaper? Then you have to check your internal, already included G in big O n times, and you have to repeat it note. Therefore, equals n squared. All right. So Kruskal algorithm, the next algorithm, Kruskal algorithm using the global view. Since easy lower bound argument shows that every edge must be looked at to find the minimum spanning tree and the number of edges, so n squared, in the fully connected, and Prim's algorithm optimal on dense algorithm. So what is the difference between dense and sparse? When it is dense, which one should I choose? When it's sparse, which one should I choose? A, B, Prim's, Kruskal, Prim's. What's your answer? A on B. If your graph is dense, which one should I choose? If your graph is sparse, which one should I choose? A. Why? Jonghoon, why? I can hear you while you're talking. Jonghoon. Nice to mute.
Is it slide say the Prim's algorithm is optimal on dense graph?
So is it Jonghoon speaking?
Yeah.
Okay, so can you say that again, please?
So I think the slide says the Prim's algorithm is optimal on dense graph. So I said.
Okay. Any logical support? Who has a logical support and why? Any guess?
Can you say the difference between dense and sparse?
Okay, dense meaning in the extrema dense meaning every vertex is connected to everybody. Dense means everyone connected to everybody. Something like this. Sparse meaning they are sparsely connected. Something like this.
Is it because Prim's algorithm just looks at the local view while like the Cruxell's algorithm looks at the global view, and it just checks for every single edge, and it becomes very inefficient in dense graphs, Cruxell's algorithm. And Prim just looks at the edges it's connected to and finds the least weight or something.
All right, perfect comment. Is it Roshan?
Yeah.
So you are so shy so far. Why are you so active today and with the clever comment? What happened to you? All right, thank you, Roshan. Great comment. So, difference between dense and sparse. What's the Kruskal algorithm mostly compute? All the edges. Prim's algorithm care about its fringe list. The most computation comes from fringe list. Kruskal talk about the global view, meaning I have to care about all the edges. So all the edges are big. The number of all the edges big. Then my computation is exponentially grows. When it is dense, Prim's algorithm only care about its fringes. So I'm only solving the sub problems. Therefore, when it's dense, Prim's algorithm is much efficient. Sparse when your graph is sparse, Kruskal algorithm works better. Clear? Okay. So Prim's versus the Kruskal versus Prim's algorithm. So one advantage of the Prim's algorithm is that it has a version runs on the n square, and consider it's based on your the implementation. Consider graph with the n vertices, and it is a complete graph, meaning all vertices are connected to everybody. And it still works on n square. The Kruskal algorithm runs on big O n m, and in the worst case is n square. We talked about this, right? So all the vertices are connected to everybody, which is n square, while Prim's run on n square. So n cubed versus n square. So version of Prim's can be used when it is dense. Okay. All right. So choosing local best is sometimes better than having global view. Why? To have a global view, it requires much computation. Okay. So Kruskal algorithms, every edge is considered only once. So either it is selected or rejected. In Prim, certain edges are considered more than once. I have to keep repeating. So in the Kruskal algorithm implementation, we can use heap structure. What is heap structure? I only care about the best one. I only care about the minimum best, the minimum. By using a min heap, I can choose min heap, go to next best, next best. So heap implementation is very efficient because I don't maintain the tightly controlled, but I maintain loosely controlled, loosely connected. So based on how you design and how you implement it, the Kruskal could be very fast. Okay, so Kruskal algorithm in action. So by having global view, I'm choosing 2 and 2. Let's say I'm choosing this guy's first as a tie break. You can choose either one of them. Then 2, then my next says 3. My next says 4, but 4 is illegal, meaning it is not safe because it creates a cycle. There is another 4. Okay, that is okay. And there's 5. 5 is actually not in my graph. Okay, then there's a 7 and 7. Then I can connect it. Meaning this process is called union. Union means 2 vertices, a 2 tree is converging. Combine 2 tree into 1. We call it union process. It is only possible in Kruskal algorithm. In Prim's algorithm, you have to be member of the graph G and keep extending it. There's no two graphs. But in Kruskal algorithm, you may concatenate two different trees into one. That process is called union. With that union process, you can implement the MST in a much faster way. So Kruskal algorithm is correct by the contradiction. So if the Kruskal algorithm is not correct, there must be graph G where it does not give the minimum spanning tree. Okay, it's the same thing. So if there must be at first as XY, the same example that we used here. Remember this. XY as such that there's a set of edges cannot be extended into minimum spanning tree. What do you mean? Then when we add X and Y, and there's no path between X and Y, or it creates the cycle. That it doesn't make sense. Therefore, it is reproving by contradiction. By adding XY to the optimal tree, it must create the cycle, right? So, but at least one edge in the cycle must have been added after an XY. So it must have the heavier, or it create the cycle. So therefore, deleting this heavy edge leaves the better MST and the optimal tree yielding the construction. So let's say graph, there's new connection. Let's say there is an X and Y connection, and there is V1 and V2. Say if this is not MST, but it is edit, meaning it will be violate my cycle limitation, or if there is another path, then by adding this should be removed, right? If not, this is not MST. Therefore, Kruskal algorithm is correct. So how fast is the Kruskal algorithm? So simplest implementation. So I have to sort all the edges, which is m log m time, all your edges. And for each edge in order, test whether it creates a cycle, meaning am I safe to do? So if it is so discarded, so if it creates a cycle, the forest we have doesn't so far, meaning then I have to discard it because I create the cycle. Else add to forest. With the DFS, BFS, or DFS, it could be done in n time. What takes n time? It's checking a cycle, right? And total time of, so I'm checking all. So first I have to sort my edges. From my edges, the smallest to the biggest, then which is for M loop. Then what do I do? Check safe in constructed graph G. Then this process takes big O n, therefore m by n. Computation m by n. Therefore, m log m plus big O m by n, which is big O mn. All right. So fast component test give fast MST. So if this process is faster, I think I can make faster. Kruskal algorithm builds up the connected components. Any edge where both vertices are in the same connected component, they may create the cycle, right? Which means graph, and there is you can dig. If the coming edge, the next order edge is inside of my constructed graph, meaning they automatically create a cycle. So if we maintain the which vertices are in which component is fast, we do not have test for cycle. Meaning, rather than testing a cycle, I'm just checking is it member or no? Is it member of no? Oh, I can make a faster Kruskal. Okay, so same component V1 and V2, the two vertices V1 and V2 lie in the same connected components. the graph by checking it and merging in C1, C2. Merge the given pair of the connected component into one component. So meaning by merging it, I have to disconnect it. Say, so if I merge them, merging this process, components C1 and C2, then this one has to check, am I create the cycle or no? But is it meaning same component? So in a forest of trees, I'm checking my tree and tree and tree, right? In the tree, I don't need to check all my cycle, but I only need to check is it my member or no. So checking same component, and when you do merge component, I can merge them with the one component to the others. If there's multiple, then meaning it violated the first lemma, right? Then the 1 and 2, then we can make a faster component. So how do you implement the fast Kruskal algorithm? So put edges in a heap, the min heap, right? So count is 0. If the count is smaller than n-1, the count start at 0. If the count start 1, then it should be n. So go to the next edge because it is sorted. If component and component is not the same, they are not in the same, meaning I just check is it safe or no. Then I can add it. If not, then now you are the same member. So we can test the components in a big O n time, the big O log n time. We can test MST in m log m, vector m log m. So we talked about m log n or m log m. Which one is better? This is better because m is usually bigger, right? Then we can test component of log n. How can it check it? Is it my component? Is it my not component? Why? Because I'm in a heap competition. So I don't need to pat everybody. I can quickly run through my height, which is log n. Is it my member or no? Is it my member? Okay, so heap, we are not tightly maintaining it, but I can see who's smaller than my parent or no, right? Therefore, I can compare my height, which is log n in the graph. Then I can be faster. So union find. So in the Kruskal algorithm, I have to merge 2 trees into one. So in the prims, there is a tree concept, but in the Kruskal, there's forest concept. Forest, there is a multiple trees. So how do we merge 2 trees into one? We call the union find program. We need a data structure for maintaining sets, which can test if the 2 elements are the same and merge 2 sets together. So these can be implemented by union and find operation, where find operation is return the label of the root of the tree containing element I, then walking up the parent pointer until there is nowhere to go. So your parent, the top of parent, meaning your tree's the root is connected to existing graph. Okay, then union ij, meaning link the root of one of the trees to the root of the tree containing others. So this component, this tree 1 and this tree need to be merged. How can I merge? Okay, they are connected. Then T2, T1 become one of the T1. Okay, so it is possible because it is heap implementation. You don't need to completely fill all the members. Then you can reconstruct this by heapify. Okay, then this process, merging 2 tree, is called the union find. And the checking the component test is find in SI and find in SJ. Okay, meaning set of SI, T1 and T2, you can quickly checking and merge them together and make a union of them. Okay, so union find tree is we are interested in minimize the time it takes to execute any sequence of the unions and find. A simple implementation is to represent each set as a tree with the pointer for node is parent. Oh, what do you mean? Pointer is node parent. What is this? So each element is contained in the node. The name of the set is key at the root. So 1 is root itself. 2, 4 is root. Go to 4. 4 is root itself. 3 is root itself. 5 is 3 is a higher parent. 6 is 4 is higher parent. 7, 2 is higher parent. Okay. So if I have to merge them together, then if I want to merge these two, then this one, new candidate is selected, 7. Then I have to merge 7 to 3. Then I do heap apply. Okay, proper union of them. So I maintain this process. Then I don't create the cycle. Then, so in the end, I will end up with the only 1, 0. Then I can complete my tree. So I'm checking if there is a 0, then I keep repeating. Okay, all right. This is what I prepared today, and hope you understand the MST and prims and cross-code. Okay, so I made a proper example, and for the code testing for this for these lectures, then you may understand better by practicing it.